also have Evan Wong, who is a mechanical engineer by trade, and his title is the Engineering Leadership Development Program Associate at Lockheed Martin. Sorry. Oh, hey, Marie. Sorry, I just saw your message. So if you would like to speak briefly about Lockheed Martin, that'd be wonderful.
Hi, everyone. I'm Marie Weber, and Evan was nice enough to invite me because I wanted to see how he walks through his new tool to share with you. So I'm excited about that and here to support you, Evan. Whenever you're ready, you jump in and cut me off, but I'll provide a little extra information while you're getting ready. So Lockheed Martin is very interested in STEM, and we want to appreciate all of you. I know teachers spend a lot of their extra time doing extra things for students, so thank you for being here tonight. From a STEM point of view, like I said, we're heavily invested and we want to encourage you.
But thank you, Marie, for supporting that.
Yeah, thank you.
Great, thank you.
So I guess just a quick overview of who I am and how I got here. I went to school for mechanical engineering, and then out of college, I got into Lockheed Martin's Engineering Leadership Development Program. So that is essentially developing technical talent for the company. So that's like a 3-year program. I'm in my 3rd year right now. So I've had the opportunity to kind of rotate around to different programs and see different sides of engineering. In my free time, I like to spend a lot of time outside. You kind of originally from Colorado, so like mountaineering and stuff. And the bottom right picture is me in my lab when I was doing research in undergrad. But I'll go into a little bit more of that in the future. So my path in engineering and STEM really started when I went to college. My high school didn't really have that many opportunities for me to get involved, I guess. I've always kind of like enjoyed math and sciences, but it really started when I went to Colorado School of Mines and started mechanical engineering. Another fun thing is I wrote for the school newspaper when I was there for 2 years. So that was actually my first job. So that kind of provided a good soft skills background. And then moving into my first engineering job, I worked for a startup up in Boulder. So there we were designing concrete wind turbines. So one of the main challenges with wind turbines is that you can't transport the towers, as you can see on the left side. So our concept was that you build the bottom of the tower where it needs to be the widest on site with concrete instead of trying to transport these massive tubes. Moving into my next thing, I showed you a picture of like my research. So I was doing research in fuel cell sciences. So the idea there was that we could use fuel cells to create fuel as like an energy storage method. So excess electricity off the grid or from renewables could be chemically converted into something like methane or hydrogen gas, which could then be burned later. I also think that technology is super cool because the chemical reaction, it involves hydrogen, which is a fuel, oxygen, and water. So it actually, fuel cells play a relatively large role in getting us to Mars and maintaining an environment out there and synthesizing fuel to get back. So that was kind of my undergraduate. And then going into, after graduation, I was kind of looking for something different and growing as an engineer and going to grad school. So I started the ELDP program out in Denver. So there I was supporting the SIG Recon program, which supports the U2. And what I was doing there is I was building the server rooms on the ground that were processing all the information that was collected from the plane. And that was interesting because it's a really old program, and learning all the engineering processes that have been in place and how they've been adapted throughout the years was a very useful insight. And when I was there, I started Cornell. So I'm still in my Cornell's master's program. I have like about a year left there. So I'm doing that as well as working at Lockheed Martin. And I also had the opportunity to move out here to Seattle, where I'm located right now. to work on the directed energy programs, which was an interesting change going from a very old program to this new research and development and a lot of new programs. And I'm going to kind of transition into that in my current work right now. So my current work is I've been doing a lot of optomechanical design to essentially package and protect and align the optical systems that we use in some of these platforms that you can see. I've had the opportunity to work on various programs. We're essentially in the initial stages of implementing our high energy laser systems on different platforms. It's really exciting work. It's been really fun and definitely very challenging. So I guess I'll go in a little bit more into that. The video didn't load, I guess, but this is our laser truck that we have our interns build every year, and we actually have our interns add on to this small system. And it's really representative of like something that we do where we build this green box that has like the laser control and the laser and the power source. And you have to implement it onto an existing platform, which in this case is just an RC car. So this is rather representative of like what we do, definitely at a smaller scale and a little bit lower risk for the interns. So getting a little bit more into the nitty gritty and like what I find interesting about my job is the optomechanical design, which I didn't know existed when I was in college, but it's essentially this weird hybrid of the mechanical engineers having to package and align very precisely these optical components. So on the left side, I took a cross section of like a camera, and as you can imagine, there's a lot of optical processing that's involved there, and just how intricate the camera is designed to allow for us to zoom and focus and things like that. So it's been very nice to learn about like the optics of it, as well as apply my background in mechanical engineering to put everything together. So it's been really nice to grow in that way. On the right side is a little bit more of what we do at Lockheed Martin up here in Seattle. This is essentially a picture of one of our lasers going through optical processing. So as you can imagine, the optical engineer designs most of the system and the processing and the filtering that needs to take place. And then our jobs is to essentially design and build the components to hold the optics and laser diodes and the fiber precisely, to test it, to make sure that it survives what the system needs to survive. And that's kind of what I do on the day-to-day. So the next thing I was asked to talk about is skills that I use every day. So kind of my bittersweet surprise going into engineering and trying to only do math and sciences is that you have to communicate every day, which involves writing and reading, which I didn't really particularly like in school. But now that I'm in the workforce, it's like a necessary skill. It's probably like one of the most necessary skills, even though people normally gravitate it to kind of get away from it. You just can't. The other skills that I use that are a little bit more technical is heat transfer, solid mechanics, and statics to essentially understand how the external environment acts on my parts and systems. So that's kind of like the basis of my undergraduate degree and how I'm using it. And then one thing that I found extremely useful is using my understanding of like the equations and just like basic linear relationships, which kind of can get applied to lower levels of math, where somebody asked me how large like a wire is or how large a cable is, and in order to increase its strength by like double what needs to be done. And instead of going in and putting in the equation, you understand that like the radius is squared, so you only have to increase the radius a little bit to increase the area. Same thing applies to like the heat transfer and the solid mechanics equations. Just having a basic understanding of how like your temperature changes as you increase area or other design selections. So the next thing I have on here is learning new software programs. You're often asked to tackle, I've been often asked to tackle things using different software programs that I've never seen before. And they kind of expect you to be able to kind of easily jump over to that, even if you don't have any like formal training. So that's being a continuous learner and being able to adapt and do my own research on something that really isn't part of my job, but like is implicitly implied. I kind of do that research every day. And then the other one is just basic organization. As you can imagine, there's just like so much information that goes into a design, and making sure that if somebody asks a question like months later, that you can pull up a document and say, this is why I made this design decision, and these were the consequences of the design. One thing that I've heard is if it's not documented, then it's not done. So I guess earlier on in like my undergraduate, when I was doing a bunch of engineering work, is do the homework, throw away the homework, as opposed to saving it and being able to use it as a reference for later. And organization is something that I've built as a skill at Lockheed Martin and continue to do so. And it's extremely useful. So the other thing that I was asked to talk about was how teachers like yourselves can support students. So the first thing that I do when I go into schools and do STEM events is I try to frame the STEM events and projects with this engineering design process, which is essentially, the first thing is understand the problem, really break it down, explore all your design choices. So you have like a very large design space, quickly build a prototype, test the prototype, and then see what went wrong. And instead of spending a lot of time building a prototype and brainstorming, trying to go through this quickly so you can see what happened during the test and then re-enter the brainstorming phase. So like my story is, when I was like in elementary school, we got a lot of design challenges to build like ground vehicles that were powered by the wind and us blowing through straws. And we got the materials to like go do it, which was great because I enjoyed building things, but this design and test process wasn't really conveyed. So I think that's something that I would have enjoyed, and I think it would be nice. The other one is framing math with real world applications. Going back to just understanding linear relationships, and my experience of algebra is just seeing lines on charts instead of seeing how it directly implies to, say, like a heat transfer problem or some sort of, or like the strength of a cable. That misconnection, I'm gonna say, encourages students, like kind of pushing it off to the side as something maybe not important. And then the last one is encouraging inter-school collaboration. So when I'm growing up in Colorado, my high school district, there's a bunch of different high schools. Every single one had a very unique STEM program. So like one was like biomedical, others were like mechanical and robotic. And I think if there were stronger connections between those students and those programs, students can maybe go to different schools to really explore different disciplines of engineering with their club experiences, as well as you could potentially drive students to really pursue their passion and get that experience before they go to college and make decisions on what they want to study. And I was kind of rushing to get my slides together, so I'm not sure if I'm going to be double touching what Marie was mentioning. But the first thing that I have on here is this optics simulator. So it's a you can just Google and write optic simulator. It's from GitHub. It's free. It's access to everybody. It essentially allows you to replicate different like light sources, different lenses, different mirrors. So we built a virtual activity using that and comparing it to things like solar collectors, how the eye works, how a laser diode works, things like that. And that kind of transitions into the virtual STEM events. So I sit on like the STEM council for my site. So my role is to build relationships with students or with teachers and school districts, and to set up generally hour-and-a-half long timeframes where we come in, give a presentation, and walk through an activity. So if you would like to potentially put something on the calendar where my volunteers could come in virtually, definitely just send me an email and I'd be happy to support that. The second one, Marie might have talked on, but as part of like the larger Lockheed Martin Corporation, there's a group that has been running like a virtual computer building learn program where essentially there's a bunch of videos and modules where students can learn about how to build like a computer. And then the students get paired with like Lockheed Martin employees and are asked to share why they selected their components. Is it for like gaming? Is it for other applications? So they get to make their own decisions, and then they get to essentially talk with an expert about why they made that decision, maybe get suggestions. The next one I have in here is high school and college internships. So at my site, we have year-round high school and college interns. So encouraging students to look for internships, even if they aren't at the college level, I think would be very advantageous. I did hear Marie talk about the virtual Green Summit. I put the link in again, and the age range that I saw on the website was sixth grade to college students. And then the last resource I have on here is Engineers in the Classroom, which is a group within Lockheed where they actually partnered with National Geographic, and there's a series of STEM activities that range from like second grade to early high school, where there is material and instructions on how to lead the activities. So maybe exploring that would bring an extra dynamic to the classroom. And I believe that is everything that I created for this presentation. So I guess we can move into question answer section.
Absolutely. So one of the questions was, how do engineers know they understand the problem?
So the one that I've heard recently is you have to ask why 5 times. So I guess walking through would be a laser diode breaks. So you ask why did the laser diode broke, and it probably points to a specific component. And then you have to say, why did that component break? And it narrows down that focus. 5 times seems to be a lot and a little challenging, but that ultimately leads to like, well, the group made the decision for this reason.
And can I add to that?
Yeah, go for it.
Yeah. So like I'm a systems engineer at Lockheed, and one of the things that we do is communicate, like Evan said. And so sometimes we have to write a lot of documentation and then share that with the customer. Other things that you'll hear is the trend towards agile. And so it's a process where instead of spending a year to build something or 2 years and then give it to the customer, you build a little piece first and then give it to them and get some feedback. And so that iterative process is really important. And part of what Evan showed in the things that he hoped to teach in terms of brainstorming, building, testing. And Agile's a little bit like that. You know, you show a piece and it's not going to work perfectly, but at least people can test it and try it. and then you can get closer to what people are looking for. So there are a few different ways to know that you have it, right? It's hard to know that you have it exactly. But there are, communication, documents, writing down requirements, communicating your ideas, but then just starting somewhere and letting the customer see it and go back and forth.
That's a great point, Marie. Thank you for adding that.
Yeah, any ideas for what sorts of projects might be good to use during remote education and distance learning?
So, I mean, that's something that we've also been struggling with, trying to do virtual activities. What we decided to do at our site is we decided to do activities that require like common day materials, maybe like a cork and like toothpicks and paper. So there's an activity in Engineers in the Classroom where you build a wind turbine to collect wind off of like a house fan. We built one with this optic simulator, as I mentioned. It's a hard challenge.
It's a very hard question. But certainly, and I might email you to pick your brain a little bit. Since we've already tried to do some of this, that's something that we're very, certainly trying to get to our teachers as well. How do we do activities virtually?
Yeah, that'd be perfect.
Yeah, that'd be awesome. Would love your help. So you mentioned that you are working on a master's in systems engineering. Can you talk, I guess I'm curious, what's the difference between the two, between like mechanical engineering and systems engineering?
So Marie might also be able to chime in here since she does more systems engineering. So systems engineering is more, from my perspective, is more identifying what the system is going to be and verifying that the system that was built and designed is the system that was originally proposed. So kind of that higher level, making sure that we really understand the problem. Whereas mechanical engineering has components of that. There's definitely some gray area where both participate, but mechanical engineering can get deeper into the weeds of how a system exactly works. And I think systems engineering also does more of like the interfaces between like different groups of mechanical engineers and things like that to make sure that when the two subsystems are brought together, that they actually work together. Marie, do you want to add to that?
Thank you. I think that was a great answer. I would say mechanical is probably easier to understand because you have physical things all around you. So your car, what's the shape of the body? How do the parts go together? And a lot of different details, like some of that math that Evan was showing on that slide. So there's a lot in the mechanics. I studied another branch that was related called materials engineering. So we might consider, well, which material do you pick? Do you pick a metal or a plastic or wood? And they have different properties. So that's another aspect. And then the system engineering, he really hit on in terms of the interfaces. So I love ideas and big picture thinking. So there are different elements of systems engineering and different systems you can work on. So it sounds very vague, but he hit it right on the head and said, what? So usually the system engineer will define what is needed or what needs to be built. And then someone else with a specialty, whether it's software developer or mechanical engineer, they will actually design and build it. So like the software developer will actually write the code, whereas I specialize in the user interface design of, I might draw what the web app is going to look like, but then a software developer will actually code it. So even within engineering, right, there are a lot of different specialties. And I think that's the important part Evan was saying about communication and teamwork, is that we have to work together to make big systems.
Awesome, thank you. So another question. So aside from seeing algebra in practice in geometry, which you had mentioned, Evan, I guess, are there any other sort of examples you can give that sort of go towards creating a more practical science classroom?
So I mean, I guess just stepping it up to like quadratics and cubics, and I mean, I'm sure there's a plethora of material science equations that are out there. So you could maybe frame like a semester in designing the rafter support for like a house or something like that. Progressing from like linear dimensions to quadratics with like circles, or yeah, quadratics with circles, and then maybe into cubics with like the strength of the beams. My favorite class in college was machine design, and we designed like one motion simulator the entire semester. And as we walked through the course, we were introduced to different parts of the machine design, and it kind of grew in complexity as the semester went on. And we were allowed to like reflect on what we were learning to this real world like challenge and design process.
Awesome. So I have a question here. They want to know more about heat transfer and statics.
So heat transfer is probably the most challenging thing that I do as a mechanical engineer, where essentially our high energy lasers create 30 kilowatts of power. And if laser diodes are, let's say, 50% efficient, right smack dab in the middle, that's 60 kilowatts, which is like 60 microwaves in a box. So trying to control and manage that heat and get the heat away from your sensitive components, that's kind of the challenge. And the design and like the linear relationship is designing like thermal straps that pull heat from one hot component to a cold surface, or designing a component with more surface area so you can pull more heat off of it. Things like that. Determining conduction distances from like one hot surface to the other without breaking things.
Yeah, thank you. What should I know or research in order to support future engineers in my classroom?
The most basic thing would probably be teaching like that systems engineering design process. If you wanted to go maybe the next level deeper, there's this tool, the engineering V diagram, which essentially outlines the beginning of the project, where we're really identifying why we're building it, what the problem is, and then we converge it down to how we do it, which is like the detailed heat transfer, solid mechanics. And then the last part of the V as you exit the project is making sure that what was built traces back to the original problem. So the engineering V diagram might be a good tool. Marie, do you have anything to add to that?
Thank you. Yeah, so I love STEM, so I could talk and talk and talk about it. But I know I realize there are teachers here probably that reach out to kids from different ages, and so I know we have a poster where we show the energy and enthusiasm, and then the scary part of the confidence and experiencing success, and then exposure. So I think through those different ages and different emotions, right, is I think you're already trying to make learning fun, so keep doing that. And then, you know, when people think they can't do it, encourage them that they can. That's the important thing, because, right, a lot of people don't want to do things or drop out because they think it's too hard. And even Evan, he's an engineer, and he just said things were hard, and that's okay. And the other part about experience, if you saw in that iteration loop, was that engineering is iteration. We don't expect people to get the answer right the first time. So it's kind of like you do that math problem and you get it wrong, and then you go back and you try again. So we don't want them to think that because something didn't turn out the way you expected, that that's failure. That's just something to learn from, right? We hear of those success stories like you know, KFC, right? And that recipe and how many times he tried to sell it. But iteration is an opportunity to learn and to keep trying. And then exposure, right? You know, what should you learn in order to help your STEM students? Just learn about all different types of things and expose them. You know, I talk with other people, and I think, you know, parents and adults influence young people, but you can't tell them about something that you don't know about. So like if you didn't know about cybersecurity, how could you tell a kid who's really good at puzzles and complex things and rules, how could you tell them, oh, you might be a good cybersecurity engineer? So again, we appreciate all the extra effort you put into it, and just keep learning more things and encourage them. And even along the lines of math, which I really like what Evan included. I would also say, and I know some people wouldn't like me for it, but I don't think everybody has to be great at math to be an engineer. So there are definitely, you know, like the concepts and the ideas. You don't have to be good at math if you're the person defining the bright ideas. You know, it gradually might work its way down to really detailed math that some people really love. But we want to encourage people to pursue their passion, and that it's really diverse. It's not just somebody sitting at a desk by themselves all the time. And so we need all different kinds of people and personalities. Thank you.
Awesome, thank you. And then one last question, and I fully admit this is my question. What does Lockheed use the lasers for?
The concept behind the laser is that you're essentially reducing the cost to fire the laser versus a traditional method of like a missile or something. So the case that is bounced around the office most often is the drone threat, whereas some person can go buy a drone off of the internet for $100, something like that, and the response that the military has to use is magnitudes more expensive. So coming up with something that neutralizes that cost difference. It also shoots at the speed of light. So for things that are moving fast, like intercepting missiles, it is more advantageous than sending your own missile to go chase after it. Because you turn it on and then the laser's there immediately. Yeah, I think those are probably the two clearest ones.
No, thank you. Yeah, that makes a lot more sense. And I'm sure definitely the clearest one.
Mm-hmm.
So that's all the questions we have. Thank you so much, Evan, for presenting. I greatly enjoyed your presentation.
Yeah, thank you for having me.
Thank you.